So the aim of this video is to calculate the arc length of the function y is x to the power of 2/3 from x is 0 to x is 1. So what this is asking us to do is to calculate the following distance. So I'm going to just draw the axes here, x and y, and our function is x to the 2/3, so the gradient of x to the 2/3 is going to be 2/3 x to the minus a third. So as x goes to 0, you're going to be dividing by x to the power of 1/3, which is going to diverge. So our function is going to look something like this. And this is y is x to the 2/3. And we are integrating along from x is 0 to x is 1, and at that stage of course y will also be equal to 1. So what we're going to be calculating is the length of this curve from here to here. To do this, let's recall the key formula for arc length, and that is that the arc length is given by the integral from a to b, whatever our start and end points on the x-axis are, of the square root of 1 plus, and then it is dy dx squared, square root of the whole thing, integrated with respect to x. So what I want to do now is, we know the formula, we know what y is, we know what the limits are that we should put in here and here, but I don't want to throw all of this straight into here. I want to work out the integrand, what the square root is, without at every stage having to sort of tediously rewrite the integral blah blah with respect to x on every step. I do this partly because I want to write less, and partly because I think it looks a less intimidating procedure if I just work out what this is first and then try to simplify it and only finally try to integrate it. So we have y is x to the 2/3. And that tells us that dy dx is 2/3 x to the minus 1/3, which means 2 over 3 x to the 1/3. So therefore 1 plus dy dx all squared is 1 plus, now all I've got to do is square this, so top is easy, it's 4, and at the bottom it's 9 times x to the 1/3 squared, which is x to the 2/3. So I have 1 plus 4 over 9x to the 2/3. And now I can take the square root of all of this, and I can take the square root of all of this. And when I look at this now, it doesn't look very easy to integrate, so I'm going to have to manipulate it in some way. And I think the only thing that I can imagine doing is putting everything inside the root on a common denominator. I cannot simplify the square root otherwise in any way, so I'm just going to put this on a common denominator and see what happens. So what we have, the common denominator has got to be 9x to the 2/3, and on the top I have 9x to the 2/3 plus 4, and I'm taking of course the square root of all of this. And now the square root of a ratio, something divided by something, is the square root of the top divided by the square root of the bottom. So I can get here on the top the square root of 9x to the 2/3 plus 4. And I cannot see any way really to simplify that, divided by the square root of 9x to the 2/3, so that's the square root of 9, which is 3, multiplied by the square root of x to the 2/3, which is x to the 1/3. So therefore I see that the thing we want to put into the integrand can be written like this. So we see that L is the integral, and now A is 0 and B is 1, and the square root is this ratio, and I'm just going to bring this in front, so I have 1/3 third 1 over x to the 1/3 multiplying the square root of 9x to the 2/3 plus 4, all in the square root integrated with respect to x. And as I've said, I cannot see any way to simplify that. I mean, in principle one could take out a square root of 9 from here and then have a 4 over 9 here, but I don't think that really simplifies in any significant way. So on the next slide, what I'm going to do is to rewrite this formula and then try to see how we can integrate it. So all that I've done is to rewrite the formula for the arc length, putting in our limits, x is 0 to x is 1, and replacing the square root of 1 plus dy dx squared by our result for it for this particular example. So we look at this and we think, is there anything I can do? And then we see, well, here we have the square root of this function. I can't simplify it, but if I were to differentiate this, then up to numbers, I've got an x to the 2/3, and if I differentiate it, I'm going to get an x to the minus a third. So we recognize that here we have outside, up to numbers, the derivative of the argument of the square root. So we recognize the following structure. We have the integral of the derivative of some function multiplied by the square root of the function. Now, I can always get the numbers right by just saying that here, for example, I want to multiply by, let's say 7 and divide here by 1 over 7. It's not going to be 7. So let's look now at this. This is of the form the function f of x to the power of 3 halves plus some integration constant. I've deliberately left a space here to get the numbers right afterwards. So let's see why this is the case. Well, if this function is integrated to give this, it must be the case that if I differentiate this, I get this. So if I differentiate a function to the power of 3 halves by the chain rule, I'll bring down 3 halves. I will reduce the power from 3 halves to 1 half, which is good, that's the square root of f, and I will multiply from the chain rule by the derivative of what is in the brackets here, and that's f dash of x, and that's exactly what I have here. So I'm going to get exactly this, except that I will have a power of, or a factor of 3 halves in front. So I'd better put in front here a factor of 2/3, and now when I do that, if I differentiate this, I get exactly that. So this is the structure that we have here up to numbers, and now what I'm going to do is make this a bit smaller and calculate this integral. So our arc length is going to be this function integrated, and it is going to be 9x to the 2/3 plus 4 all to the power of 3 halves evaluated between x is 0 and x is 1, which are just the limits there. And again, I've deliberately left a space here because I'm going to have to put some numbers in here such that when I differentiate this, I get exactly this. So what do I need? Well, if I differentiate this to the power of 3 halves, I'm going to bring down a factor of 3 halves. I don't want that factor of 3 halves, so I'm going to put a factor of 2/3 immediately there, so that that will cancel with this. So I'll bring that down, reduce it to the power of a half, which gives me this square root that I want, and then I'm going to multiply by the derivative of this. The derivative of this is going to be 9 times 2/3 times x to the minus a third. I subtract that power. The x to the minus a third is exactly what I want here. But I'm also going to get, as I say, a factor of 9 that I don't want, and a factor of 2/3 that I also don't want. So I'm going to put a 1 over 9, a 1 over 2/3, but that is 3/2. And now, if I differentiate this, I would get 1 times x to the minus a third times this square root. But I want this factor of a third here, so I could just put it outside, or I can put it here. Let me put it here. And now, if I differentiate this with respect to x, I get exactly that. If you're not confident with this, it's worth checking very carefully, because you really want to try to get into the habit of getting the numbers right in this way, in my opinion. So now we can just tidy this before we put the limits in. So we have that our arc length is, so what do we have? Well, the 2/3 and the 3/2 are going to cancel. And we've got 1 over 9 and 1 over 3 here. So multiplied together, that's going to give us 1 over 27 times 9x to the 2/3 plus 4 all to the 3/2 between 0 and 1. So 1 over 27 is a common factor. When x is equal to 1, at the top limit here we have 9 plus 4, and that is 13, to the 3/2, minus, and then we put x is 0 into here, that vanishes, and we have 4 to the 3/2. 4 to the 3/2 is 2 cubed, and 2 cubed is 8. We've closed the brackets there. So to conclude, what we have calculated is that the arc length we're looking for is 1 over 27, open brackets, and it is 13 times the square root of 13, that's 13 to the 3/2, minus 8. And I'll just underline our result. The reason why I think it is useful to write it in this way is because if I look here, 13 is greater than 8, the square root of 13 is greater than 1, so here we definitely have something positive, and as this is an arc length we must get a positive result. So it's always worth checking once you've calculated an arc length that yes, this is positive. It gives us a little bit of confidence that we've not done something that's definitely wrong. Okay, and with that I'll stop this video.